talking a little bit about aldehydes and ketones, some of the stuff that we talked about, which I think is also sort of the lab this week, if I'm not mistaken. So earlier we talked about obviously aldehydes and ketones, and again, the difference there, obviously our functional group there for our aldehyde and our functional group there for our ketone, which is again that sort of 3-carbon run that has a double bond there with the carbon in the middle is our ketone. Again, basically these guys end in Al, these guys end in ONE. In terms of the aldehyde, because of this group, as we talked about, again, we'll end up at the end there. We do not need a number or give the number of the carbon-oxygen double bond, and that is different here with our ketone, about 4 or 5 carbons. We do need to give the number where the carbon-oxygen double bond is to give it the smallest number. We obviously, as we did in some of those examples towards the end there, number everybody else accordingly and name all the groups, obviously, sort of in alphabetical order. So at the end there, we were talking about, 2 types of tests, which is our sort of Tollens test and our Benedict's test. And again, one really uses silver that goes to really solid silver, which again is why it's sometimes referred to as the mirror test. And one uses copper 2, which is blue, and kind of goes to copper 1, which is, depending on your preparation there, orange, reddish type color. And both of these really do signal the idea that, oxidation has occurred and a carboxylic acid basically has been made. And we use this really to sort of distinguish between whether or not, we're starting with an aldehyde or a ketone, depending on whether or not the carboxylic acid is actually formed. So as I mentioned before, the sort of process there in terms of the reaction is we have really a primary alcohol. And that again is our guy that will of a primary alcohol get oxidized through the loss of our 2 hydrogens, making our double bonded there in our H, which is our aldehyde. And it's this guy that we can further go through oxidation. And again, this oxidation is really the adding of the oxygen. I'm not sort of drawing the rest of the guy on the left there, but making here our carboxylic acid. And we don't really see that sort of continuation when we start with a secondary alcohol, like we talked about. I won't draw all the hydrogens there on the alcohol, but when it goes through oxidation, again, able to do so, making our double bond there and really our carbon there and making our ketone. At this point, when you go through an oxidation, not going to occur in this case. So when we use something like the Tollens test or the Benedict's test, and we do get that positive, which again for the Tollens would be that kind of silver color occurring, and for the Benedict's test there, it would be that orange red color. That implies that our carboxylic acid has been made, which if we sort of follow it back implies that we did have an aldehyde to start with. And again, if we just want to kind of fill this guy in, we'll just do this guy here work. And again, basically this is ethanol, as I wrote before, becomes ethanal, Al. And our carboxylic acid is ethanoic acid. Carboxylic acid ends in oic acid is how you do the end of it, based off of 2 carbons. Ethane becomes ethanoic acid. So here again, we have our 2-propanol. that ends up becoming propanone, and obviously will not oxidize it. So because this oxidation doesn't occur with our ketone to the carboxylic acid, the silver is not able to become silver with no charge. So that reduction doesn't occur, and the copper is not able to be reduced to copper 1. So that doesn't occur here when you're starting with a ketone. And that's why it's negative, and you did not have an aldehyde to begin with. So we use these, again, these two sort of tests to verify that we started with an aldehyde and we basically ended up with carboxylic acid. And again, any negative of those tests would indicate that you did not start with an aldehyde and you ended up with basically started with a ketone in that particular case. Any questions on that? Now, let's talk a little bit about, some of the reactions that we do see with aldehydes and ketones. So remember, as I just drew there, that it is our primary alcohol that you get when you have a aldehyde. So let's just say we had any aldehyde here. This looks good. So let's say we have this aldehyde and we want to actually react it with hydrogen or H2. And we want to draw the product. This reaction is really the opposite of the oxidation reaction. So what happens here is you can think of this aldehyde, and it is really only this part of it here that basically gets changed. And if you look at this, we can think back to when we had a carbon-carbon double bond and we added hydrogen. Basically, what we did is we made that carbon-carbon double bond into a single bond, and we put a hydrogen on both of the carbons. And when you have an aldehyde or even a ketone, as we'll do in a second, and you add hydrogen to it, you're doing basically a reduction reaction, which is the opposite of an oxidation reaction. And basically, the exact same thing happens here. We're going to draw everything exactly the same. The only difference is our carbon-oxygen bond will now go from a double bond to a single bond, very much like what we did here. So very much like this, except this carbon and oxygen becomes a single bond. It becomes a single bond because now that makes room for a hydrogen to be added to the oxygen and a hydrogen to be added to the carbon, just like what we did here, where we added hydrogen to each. We add a hydrogen to the oxygen, a hydrogen to the carbon, and voila, we have now went from 1, 2, 3, 4 carbons, butanol, to 1, 2, 3, 4 carbons. That's an alcohol, butanol, and actually 1 butanol, which is a primary alcohol. So when we oxidize a primary alcohol into an aldehyde, the opposite reaction is the reduction of a aldehyde into an alcohol. Works the exact same way as the carbon-carbon double bond when you add hydrogen. The only difference is this is the carbon-oxygen bond that becomes single bonded and we add the hydrogen in. Works the same way if you had like a ketone. So let's do one of those guys and see how that all works. Let's do this. Now, if I added H2 to it, which again is 2 hydrogens, addition reaction, also a reduction. Absolutely nothing changes in that big old molecule except for our carbon-oxygen double bond. Just going to become a single bond, again, very much like this. And all we have to do is copy what's there, which would be CH3, CH2, CH2, carbon, oxygen, single bond now, CH3. Again, just like what we do with the carbon-carbon double bond, we're going to turn that into a single bond to make room for each of these hydrogens basically to come in. One again will come to the oxygen, one will come to the carbon, and now we have our alcohol back. And this would be 1, 2, 3, 4, 5, 2 pentanone becomes 1, 2, 3, 4, 5, 2 pentanol, which is a secondary alcohol. So again, this is basically the opposite reaction to what we see happen with our secondary alcohol that gets oxidized to a ketone. We could put the hydrogen back in, which is the reduction reaction, and take our ketone back to a secondary alcohol. Same thing can occur up there with our aldehyde back to a primary alcohol. So this is basically an aldehyde back to a primary alcohol. And this is a ketone reduced back to a secondary alcohol, which is basically the opposite reaction of oxidizing our alcohols. Question on either of those two there. All right, so why don't you try one here? Let's say R2. Let's say we have this. I draw the result of that, and let's do this. All right, take a moment and see what you come up with. Draw the result here of each of these. Okay, so remember in all these sort of reactions, there's only really one spot where anything changes. And in this case, it really is our carbon-oxygen double bond here. In this case, it's going to change just like our carbon-carbon double bond. We're going to make a single bond. Everything else exactly the same. Nothing else changes. So just going to copy what's there. Going to turn that into a single bond. And okay. That is because here we're really adding 2 hydrogens. And by making that into a single bond, we now have room for them. And we would put a hydrogen here and a hydrogen here. Again, in this case, going from a ketone to a secondary alcohol in this case. And that is what we end up with. Any questions on that one there? Same thing here. This is an aldehyde, but in this case, this reaction, which is a reduction reaction, all going to revolve around that carbon-oxygen double bond. Exact same deal. We're going to turn that guy into a single bond. I'm really not going to think too much about the rest of the molecule here. I'm just going to copy it, turning my double bond into a single bond at this point. And now I have room for each of those hydrogens that are going to come in. One going to the oxygen and one going to the carbon. And again, this would be our aldehyde to our primary alcohol. Any question on that? Again, those are both reduction reactions. Remember, one of the major definitions of reduction is the adding of H2, which is essentially what we did here. And that is the opposite of oxidation, which occurs as we go in this direction, the removal of H2, right? Same thing here, oxidation going in this direction would be the removal of the H2 to make our aldehyde. So again, the reduction and oxidation are opposites of each other. In this case, between ketone and aldehyde, adding H2 does the reduction reaction for each of them, and removing H2 does the oxidation reaction for each of them. Any questions on either of those there? Okay, then let's talk about a reaction that aldehydes and ketones will undergo when alcohol is actually added to them. So let's take a second or two here, probably a little more a second or two. Let's talk about two sets of reactions that occur. And basically when we take a aldehyde plus an alcohol, and in some cases plus two alcohols here. All right, so we'll do one at a time. So let's just take a random here aldehyde. I'll just draw one up. Why not? That looks good. And let's add to it one alcohol. We'll just do a nice simple methanol. So this is methanol, one carbon and an OH group. So basically methanol and 1, 2, 3 propanol in this case. So when you take an aldehyde and you add an alcohol to it, they will come together to make something that is known as a Hemi Acetal. And what's going to happen in this case is the alcohol here, methanol, the alcohol will add basically kind of in two sections. And the two sections of the alcohol is this guy here, this oxygen and carbon group. And the other part of the alcohol that's going to add is the hydrogen. So we're going to add both of these things into a specific location, and the specific location might not be a surprise to you. It is the carbon oxygen double bond. As you could probably see here in these examples, the carbon oxygen double bond is pretty much where all the action sort of happens when aldehydes or ketones sort of react. And what's going to happen in this particular case is we're going to get an addition reaction. And what that basically means is we're going to do the exact same thing we just did to this, is we're going to make room for it. And to make room for it, we need to basically make that into a single bond. So what will happen is everything will be exactly the same. The carbon oxygen bond will now become a single bond. Not sure why the oxygen is so much bigger, but we'll just go with it. And basically what's going to happen is the H is going to come up into this guy. And then this guy right here, this oxygen carbon group, will actually go into the carbon. So just like what we did with the two hydrogens, where the oxygen got a hydrogen, the carbon got a hydrogen, same thing happens here. Hydrogen goes to the oxygen carbon group goes into the other carbon, and we get a structure that looks something like this. An OH group is made up there, and into this guy goes our oxygen carbon group. This is what is known as a Hemi Acetal. A Hemi Acetal has a couple of features. First off, it has, when we look at the features and we look at the carbon, that's sort of where our double bond used to be. Attached to that carbon, we will see several things. First off, we will see one oxygen hydrogen group, which we see up here on top. We will also see attached to that carbon one, I guess I should do that instead of two. We'll see one oxygen carbon group, like we see here. And attached to that carbon, we will see a hydrogen. And those are the main parts of what makes up a hemiacetal. The carbon oxygen, the carbon has an OH group attached to it, a hydrogen attached to it because it comes from an aldehyde, and an oxygen carbon group. And that's how you could recognize it as a hemiacetal. Any questions on that there? Now, this hemiacetal that we just made, so I'm just going to redraw it below. If you then add another alcohol to it, so we'll just use the same alcohol. It doesn't necessarily have to be the same alcohol, but we'll use the same alcohol. So again, here we're taking another alcohol and we're adding it to a hemiacetal. We get sort of the similar process occurs here. We are going to get water that's going to form. And the water is going to basically come from here. H2O. So that is where the water is going to come from. So we will make water. I'll just highlight it here. H2O coming from there. Now, if you think about it, this guy has now left. So basically this guy has come off. This guy comes in with it to basically make our water. And we're left with the exact same thing that was there, obviously, except for the OH. And what else is left? It is our same oxygen carbon group as we saw previously. This guy will then actually go into its place and go right in there. And we will end up with this second oxygen carbon group that's attached. And this is what is referred to as a acetal. So if you take a hemiacetal and add another alcohol to it, you end up with an acetal. And what does an acetal sort of have in common? It has basically two oxygen carbon groups, which are, this guy and this guy. And it has one hydrogen, which is obviously this guy right here. It does not have any OHs, so that's why it's not called hemi. Hemi, you can think of is like there needs to be an OH involved. Acetal, we don't have an OH. So this is a reaction that occurs with an aldehyde and an alcohol. If you add one alcohol, you basically get what is known as a hemiacetal, which should have three major components. Should have an OH group attached to that carbon where the double bond originally was. It should have a hydrogen because it came from an aldehyde, and it should have an oxygen carbon group like we see here as OCH3. If you then take that hemiacetal and add one more alcohol to it, water will be made and the OH will come off. And the second oxygen carbon group will be added in its place. And that's what we see there at the very end. We end up with two oxygen carbon groups and one hydrogen. Any questions on that reaction there? Now, ketones actually do pretty much the exact same thing. So let's just take a look at a ketone and see how similar it is, maybe how different it may be, and some of the differences. If we were to take a ketone and add one alcohol to it, we would get something that is referred to as a Hemi. Write that, Hemi Ketal. So let's take a look at what something like that might look like. Let's just take a fairly simple-ish ketone. Let's Nice, simple little guy here. And let's add an alcohol to it. And we'll do like a ethanol. And in this case, much like the aldehyde, we see that carbon oxygen double bond. We know everything that's happening pretty much right there. And we're going to make that carbon oxygen double bond into a single bond like we did previously. And if we do that, we end up with CH3, C single bond oxygen, CH3. The reason we're doing that is so that we could add our alcohol. And again, our alcohol will actually come in parts, which means we will have an H that's going to be added, and then our oxygen carbon part, which would be this part right here. So the H, just like before, will end up where the oxygen is. And the oxygen carbon group will end up at the carbon. Good way to remember that is H to OH, oxygen carbon goes to the carbon. So the guys that have the carbon end up at the carbon. And when we do that, we will end up with our OH group here. And then our oxygen carbon group will attach right here to the carbon. This again, it becomes what is referred to in some circles as a Hemi Ketal. The key points of this is it has one oxygen hydrogen group. It has one oxygen carbon group, which in this case is this guy. And different than the Hemi Acetal is no hydrogen on the carbon. And what I'm talking about is this carbon right here. There is no hydrogen. If we go back to our acetal, or hemiacetal, there is a hydrogen here on this carbon. And that is because the hydrogen came from the aldehyde, which is not present in the ketone. So that's how you can tell the difference between a Hemi Ketal and a hemiacetal. They both have OH groups. They both have an oxygen carbon group, but it is only the hemiacetal that actually has the hydrogen on that carbon. If there is no hydrogen, then it is a Hemi Ketal. Any questions on that one there? Now, just like the other, we can continue this process and add another alcohol to this Hemi Ketal. And in this particular case, we'll add a different alcohol. Let's just do methanol in this case. And exactly like what we did before, so we have our alcohol and our Hemi Ketal. Just like before, we're going to lose water here. So what's going to happen is our OH here and our H are going to come together basically to make water. Yeah, so it's going to come together here to make our water. Again, our water being made from that. And this part right here will then take the OH place at the carbon, and everything else remains the same. So this guy, this guy, this guy looks exactly the same. Nothing changes. This guy was there originally, and now we're ready to put this guy in, and we end up with an oxygen carbon group. And this is what is referred to as a ketal. Basically, two alcohols added to a ketone. And what this guy has is two oxygen carbon groups, which in this case we'll just call oxygen carbon groups. And again, no hydrogens in this case. So if you take a ketone and add just one alcohol to it, you get what is referred to as a Hemi Ketal. That has the OH group, hence the name Hemi, if you wanted to remember it that way. Oxygen carbon group and no hydrogen. If you take a ketone and add two alcohols to it, you will end up at a ketal. And kind of the same thing with our aldehyde. If you add one alcohol to it, you end up with a Hemi Acetal. And if you add two alcohols to your aldehyde, you'll end up with an acetal, which should have two oxygen carbon groups and basically water in that particular case. Any questions on these two reactions here? Hopefully you can see kind of the similar things occurring. Again, that carbon oxygen spot on the aldehyde and the ketones are the really important spots, pretty much where everything sort of takes place. Any questions on that or other things we've been talking about here?